Okay. Hi, everybody. This is lecture number 9. This lecture and the coming one will be implemented using LabVIEW environment only. Very often, while working with LabVIEW and Python, it is required to convert data from Python environment to LabVIEW environment. There is a direct common way to do that by using Python node in LabVIEW. Another simple way to do that is to save the required Python data as CSV file in Python, and after that to convert the CSV file in LabVIEW, because LabVIEW can open and convert the CSV files as strings or as containing data as strings or containing data as double precision values. In the previous lecture, you remember, we worked with Python curve-fit function, and we have solved several examples. One of these examples was this one example, which I will show you now, where I saved the X and Y arrays as CSV files. Here, look. In this example, which we have discussed in the previous lecture, I have used Numpy SaveText function. I saved it as with a name Samara CSV. The array was x1, and the other array, which is x2 also, was saved there to be used in the regression process. And also at the end of work, we have got the predicted values as an array, and this array was called yPredict. I also saved this yPredict function as a CSV file. This was done specially so that when I read this lecture, I will refer to them as I have done just now and continue our work with LabVIEW. Why I have done that? Really, it is always necessary because of many reasons to convert data from Python to LabVIEW or from LabVIEW to Python. In this example, I shall you convert the Python CSV file to LabVIEW file, two-dimensional file, and make use of this data to make a three-dimensional plot. Remember, we have made three-dimensional plots using the three-dimensional 3D graph in LabVIEW, and we found that this facility is really very simple and easy to use. Maybe it is easier to work with it than to work with Python plotting packages. So here I right-click on the front panel, as you see. Here is the graph. Here is the 3D graph. And here you have options, different types of three-dimensional plots which could be done by LabVIEW. These include parametric graph or line graph. I have used both of them here. The front panel now will look like this. This is the Read Delimited Spreadsheet.VI. This virtual instrument, here it is, and file input Read Delimited Spreadsheet.VI. This VI is used here. It requires the path, which contains the address of the file which is going to be read. This path here is really the path where I have written the Python arrays. The first one, which is X1, called Samara CSV. The second one is X2, which was called Alien CSV. And the third one, Prediction CSV. If you want to look at them in the system, you go to the PC, to C, and users, and to Dell, and here you will find these CSV files already. Here is Alien, for example, CSV file. If you go down to the letter of S, you will find Samara, and then we will find Prediction one also. This is Prediction CSV, and Samara is outward. So as you see, these files exist in the system here, and now I want to make use of them to read them by using the Read Delimited Spreadsheet.VI. Here it is configured to read double precision values, so this color is yellow, and the output, as you see, is a two-dimensional array. If you look at it here, okay, it is not read yet. So the two lines here are sufficient now for us. Here they are. So this is the first array X1, which is Samara, two-dimensional, one dimension, two dimension, but one column, the other one, and the prediction array. The three arrays are available. So the three arrays now are read, and they give data here. This data now is taken and reshaped to one-dimensional array. The three, each of them is converted by reshaping the array to one-dimensional array. The number of the elements in the array is 100, so reshaping here requires to put the number of elements, which is 100. I put 100 here, 100 there. So the output here, the size will be 100. If you look at it here, it is 100, and this is 100, and this is, all of them have the same length. Okay, so now I have 3 one-dimensional arrays. They are now fed to the create plot line VI, this VI, which is shown here. Now, if I run the program here, you will see this is exactly the same shape of the regression function which was produced by using Python. Also, you can see it here, the same thing by using the other VI. Here it is create plot parametric VI. This is the parametric VI. As you see, the same figures directly appear and are shown without any difficulty. So in summary, what I wanted to tell you, I wanted to show you through an example that we can save the data in Python as CSV file, and this CSV files could be read in LabVIEW environment, and now they could be treated and used by several functions available in LabVIEW. And we have, as you see, I have shown you this example for this purpose. Okay. Now let us move to another example. I will show you now another example in LabVIEW. Of course, in the field of regression of nonlinear functions. We are still in the nonlinear function, and this is really important because, as you see, the nonlinear gives more flexibility, and most of the relationships between the dependent and independent variables are nonlinear. So nonlinear is most common and should be understood and treated by us. This is another example here. I will show you the block diagram at first, talk about it, and then we will tell you how it works. So here we are using nonlinear curve fit VI. This is a LabVIEW function now. Nonlinear curve fit VI. How to find it? You go to mathematics, fitting, and then you go here, you will find nonlinear curve fit LM. If you select the option nonlinear curve fit LM formula string, you will come to the option which I'm working with. So here we have 2 options with this function. In this lecture, we shall work with the second option, and in the coming lecture, we shall work with the nonlinear curve fit only. So we are now here. We have the algorithm or the function of LabVIEW. How it works, what does it contain? If you go to the help, where here there is no help for this function, but really you can go through the help of LabVIEW and find shortened information about it. So what is the inputs and outputs? The most important things which I showed, which is necessary here, the first terminal here, which must contain the function which is going to be optimized, or where we can find the regression, which is called Y input. The other input is the X input, which represents the variable or variables if they are more than one. If they are more than one, they have to be concatenated in one variable x. So this is the variable x. It is like an array of values, and this is the y array of values. Here you have an input now, which is really representing the input mathematical formula as a linear or nonlinear function. Here I am working with a linear now, with a nonlinear expression. The first coefficient here is A1, free coefficient. The second coefficient A2 multiplied by the variable x. X here is the array at the input. And the third term here is A3 multiplied by x squared. So I have x squared, so this means that this function is now nonlinear. The coefficients A1, A2, A3 must be arranged with the same sequence here within this terminal, and the name of the variable x must be printed here. So in the front panel here, this terminal is this terminal here. Why they're broken here? I think because I have forgotten in the front panel, I have forgotten maybe, yes, because I have forgotten this function unconnected, I have to delay it. It is deleted. Okay, so now we have input y, input x, and the input terminal, which represents the model mathematical description. These are the most important. And also here we have a special interesting input, which is the initial guess of parameters. You have to give an initial guess about the values of the parameters, critical parameters, which describe the data set or the model function. Here it is important to note that this function behavior and correctness depends, of course, on the initial parameters. And the engineer must, as much as possible, select them close or near to the true values. Otherwise, the process could be not convergent and it will give errors at the result. So this is important to note. So this is an array, the values which you suggest as initial values, you have to input it here. I have, as you see, 1 term, 2, 3 terms, so I should have 3 coefficients here, and this is all about it. Well, the output of the non-linear curve fit here includes the values of the parameters, the coefficients of the function, which are calculated as the best values, best fit parameters, best fit coefficients of the function. And also here you have an array which includes all the values of the predicted values of the output. So you can draw and see, you can plot and see the curve which represents the regression curve of the output. Now, in order to work, so we need to generate a synthetic set of values as arrays of x and y, and we have to decide the formula. We have to suggest the values as initial values, and then we can run the program and judge about the quality and the performance of this function also. So I suppose here that I have this data set x1 as a variable, as an array variable. x2 is another input array variable. Both arrays are built as an array, but this array is converted and concatenated to one-dimensional array. What does I mean? What do I mean? If I go to array here and build array and put it here, you will see that it could be expanded to any number of values. Here I have only two numbers, two values. If I connect this value, as you see here, and connect the other value, at the output I have to get now two-dimensional array. As you see, two wires, two-dimensional array. This is not required. I do not need it like that. I need to concatenate x1 with x2. What should I do? I have to right-click on the build array function and select concatenate inputs. Now the inputs now have changed as here. They are now different. They do not show arrays. And the output also, now as you see, shows an error because I have connected two-dimensional output. Now it doesn't work. If I cancel it and connect here newly an indicator, it will work now as one-dimensional array. This is one-dimensional as it is here. So now we know what do we mean by concatenating two-dimensional arrays in order to get one-dimensional array which is composed of the two arrays x1 and x2. First, we have the values of x1, and after the values of x1, you will have successive values of x2. I'll show you now. So at the output now, we shall have this one-dimensional array, and this array is called appended. If you look at it and look at x1 and x2, I selected values to be easily understood by you. So x1, as you see, from 1, 2, 3, 4, 5, this is sequence of values. x2, another sequence, 6, 7, 8, 9, 10. Now, if you concatenate x1 with x2, you will have this value array, the new array, begins from 1 ending with 5, and then directly it begins with 6 and continues up to the end of the x2. So this is the concatenated x, or as it is shown here again, appended array. So now we have appended the arrays, and this appended value which is going to be fed to the function. We go here, and now it is fed as x to the nonlinear curve fit.VI. The other thing which we have to do is to generate a set of data which represents the y. I have selected a synthetic values for y, any values, but I have selected them, as you see, not always increasing, from 4 to 7, then it comes down to 4 to 5, then comes down to 4, then increase, any random values. This is y. And to be near to real measurement in environment, I have to add to this y a noise. This noise is added by using continuous random VI. This continuous random VI is, I think, in mathematics, probabilities. Here it is, continuous random VI. You have to wire the inputs and the outputs, and to select here from this window the type, whether it is uniform or it is normal. It should be somewhere normal. Yes, normal, or another type, exponential, and so on. So, okay, I have now this function. I have selected the mean equal to 0, the mean value of the samples at the output. The standard deviation, I have taken it somehow high to generate an influential noise. And here 10 is the number of the samples, This is the output now, which represents a noise. The noise is added to the synthetic values of y, and now this output here represents really the y input, which comes to the function. So now we have the y input, and now we have the x input. What is left here is to put the initial values. I have selected these numbers. Also, they are selected randomly because you will see the result. If the result is not convergent or bad or with a high error, we can see the error and the goodness of the function, so you can change them. You have no problem with that. Anyhow, so I have selected these values, and now before running the program, of course, I want to be sure about the quality of the work. So I first want to see how the function looks like with the noise and how the function looks like compared with the best values fitted to the data set. I mean here, this is the output of the function. This is the best fit values, and here is the best fit coefficients. I have put here suggested values. Here I can get the exact best fit parameters. If you look at them here, instead of 2, now I have 7.68, for example. Instead of 5, I have minus 3.89, and so on. So these are the best fit values. And we can be sure, are they acceptable or not? Of course, we have to go back here and to make use of the goodness function, goodness of the fit, to which degree is this function works well, goodness function. This function requires only 2 inputs. The real input with noise, this is the real input with noise, and the output, and it compares them together, and as a result, it gives you to which degree they are agreed with each other. At the output, you will get the mean square error or the root mean square error and the error squared. Remember, error squared, we said when there is a very good quality, goodness of fitting, it is close to 1. If it is very bad, it is close to 0. In between, it gives you a maybe acceptable or non-acceptable values, and you can change it, of course, by changing the initial parameters. So, as you see here, I use the goodness of fit function. How to find it also not difficult. I told you before, you go to mathematics, you go to fittings, you go to advanced curve fitting, and here you select goodness of fit. Goodness of fit. And you connect it as I have done here. Now also I have this is a bundle function. This is another bundle function. I have bundled the x at the input and y with noise at the input. And here I have connected also x at the input and the best fit at the output, from the output, this best fit here. So now I can get here a curve. If I look at it, this is the initial spread of values with noise. Here is the curve. Here is the best fit of the curve relative to the initial values. So, of course, these values also may be shown as a continuous function. You go here, and for example, you can click here, and you will see how they are connected. You can make it as you see here, or you can leave it as it is as points. It depends what do you want. They give the same information, no different. Now, if you go back, so now we have a means to test the function. We have an idea now about the curve at the input relative to the curve at the output, and I can run the program and have the results. If I go to the front panel and I run the program, as you see, nothing has changed. What I have got? I have got here that the mean squared error is 23. R is given, as you see here, 0.825. According to this value, it is good, not bad. It is very close to 1. And the mean square error 23, it is also acceptable. Of course, as small as it is better. The root of this value is given here, root mean of square error is about 4.8. So this information is the same. When I solved this example by using Python, I have got that the mean square error was 22.88 instead of 23.15. And the R squared is 0.77, which means they are very close to each other and they give practically very acceptable values. Anyhow, we can test another values instead of 2, 5, 5, for example, but we have to remember what are the best fit parameters. We have given them 2, 5, 3. I have given as the output these values, these 3 values. If I put here, instead of here 2, 5, here we have to, it is the same here. Let me put here 1, for example, 5, 2 instead of 3. And look, what is the difference here? Is there a change will be? If there will be no change, this means these values are very close to the exact. And as you see here, nothing has changed. They are very close and they are very good. Of course, you can select a little bit far away, 4, 5, for example, 6 here, and run the program, and you will get that nothing also has changed. Only here, instead of 2, 3, or instead of 5, 8, nothing has changed. And the curve itself and its orientation is the same. Everything is okay. And the function works very, very accurately. Okay, now let us consider another case. Here I have selected that the regression curve will have a parabolic shape, a nonlinear, with a degree of 2 here. Suppose I want to work with a degree of 1. I want to approximate this data set and to see the fitting as a line. So simply I have to cancel the third term. If I cancel this term, Now I have A1 and A2, so I have to delete A3 here. I right-click in it and go to data operations, delete element. Now the third element is deleted. It seems to me that everything is okay. I have also here to change, instead of 3 values, I should have only 2 values. So I should here also cancel one of these values. Data operations, delete element, it is deleted. Now I have 4 and 5. Let us work with it and see what is going to happen. Okay, we run the program and we see really this is the original data set, and you see this is the linear fit here. And if you look at the R value now, you see it is 0.63. It was before 0.84. Now it is 0.63, which means it is a less appropriate. It is not that good as what we have when we used a third term here, or a parabolic nonlinear function. But it depends what do you want, and it depends on the character of the points here. These points here, usually, as you see, they are better fitted to a 2 or second order curved function. I hope that this is interesting and this is also clear to you. Now I leave this example and I have to go to another example. File, exit, don't save. I want to keep it as it is. And I will go now to the example 3992. Continue. Okay. Here is the block diagram. Principally, we shall see that we have the same structure. So this is the same function, nonlinear curve fit VI. I have an input Y here. Here we have input X. Here we have the formula which will fit the data set. Here we have the input with the initial values which we suggest. Also, we have to generate a data set which has values of X1 or X1 and X2 or X if we only have X. What I have done really, I have generated through this circuit here an array. This array has a size of 100 elements. It begins with 0 and ends with value 7. Of course, here they are. So the start value is 0 and the end value is 7. I subtract 0 from 7. I have the range. Divide the range on the number which I want, which gives me the step. And at the output now, I shall have, through this for loop, an array with a continuous equal steps for 100 values. Here at the output, we shall, if I want to see this, if I run the program and I want to see this array, I shall have one beginning from 0. The first step is, as you see, 0.07. The second one will be 0.07 multiplied by 2. Here is multiplied by 3, here by 4, and so on, up to 100 values. This is the generated X array. This array, as you see, I called it X here, or X1. It is this. I'm using it as X and X1. So I take it, as you see here, this X, and I take it again as another input. I concatenated them together to give us the output X. What is the difference between this X and this X? The difference is this one will have 200 elements instead of 100 elements. Sequentially, here I shall have 200 elements. Here it is, the size 200. So when I concatenated them, I have the value here for 100 and followed by another 100. The size here it is, this is the array size. You go to the array for those who are here, the array size, you put it, connect the array to it, and then you read the output to see the number of elements. Here is the size will be 200. It is 200. So this input, which is going to be fed to the X input, here, the X input. The Y input also will be a data with added noise, so that the sum of them will represent a set of data which is somehow very similar to a measurement value from real process. So I take the value of concatenated X, square it, multiply it by half, and the same thing here, and add it together. And the end, I add it with a noise, and here the output, which is going to feed our function. This is Y now. This is Y plus noise, which is feeding the input. Here I have shown you, just if you are interested, the maximum and minimum values within this array, which is the input. This is interesting. Why? So that when you select the initial values to be very in the middle, in between, within this range at least. So the minimum value of this array now, sorry, if I double click it, here it is minus 19. And really, if you go here and look at these points here, they are coming down. Oh, here minus 20. Here they are about minus 19. And the maximum value is about 190. If you go up here, 180, 190. Here, this is the maximum and minimum values. Okay, so as you see, we have now furnished the problem with the required values, except the initial guess. The initial guess is given here as 3 values. Why? Because I am suggesting here also a second order polynomial function. So I have coefficients A0, A1, A2, A0, A1, A2, and now also I have established a way to compare between Y at the output with predicted values and the Y at the input, which is at the input of the function, to get the R squared value and to get the RMS values. Here they are. So this is R. As you see, it is very high, really, 9.6. And this is the, yes, the root mean square 10. The means here, the mean square error is about 100. If I run the program now, nothing is changing. These are values, and as you see here, nothing has changed. Everything is okay. Of course, as I told you, I can change the initial guess to see that my coefficients, which result here, what are the coefficients which are at the output. Here they are 1, 2, 3. These are the best fit, and these values really are the values which represent the prediction values for every input x value here of the function, which is the red values here. So the values are C117, for example. Let me put here, instead of 2, 7, for example. It doesn't change too much? No. So we are working very well. The algorithm is strong enough, and there is no problem. You can change, of course, any other tool. For example, here you can say 5, you can say here 9, and run it. I think that nothing bad will happen. Yes, we shall have the same results, and which means that the problem is solved successfully, and we have no problem with it. Okay, I think that is sufficient today. In the next lecture, I shall give you another more example, and then we shall move forward to discuss more interesting things about this function. Okay, wishing you the best, and see you in the coming lecture. Goodbye.